Row upon row of gleaming steel and glass stretched toward the horizon, baking silently beneath the midday sun in vast parking lots across continents. Thousands of brand-new motorcars sat idle, their engines primed and ready, yet their intricate electronic systems lay paralyzed by the absence of a single sliver of silicon no larger than a fingernail. This humble window control chip, or perhaps a more critical power management component, represented the fragile thread connecting modern mobility to the invisible world of semiconductors. The scene evoked a profound sense of vulnerability, a quiet reminder of how the pulse of global industry could falter when the microscopic heartbeat of technology skipped a beat. For decades, the automotive sector had embraced the philosophy of just-in-time logistics, a delicate balancing act that minimized inventory costs but left no margin for disruption. When the global pandemic struck in early 2020, it triggered a cascade of events that shattered this fragile equilibrium. Demand for vehicles plummeted initially, prompting manufacturers to cancel chip orders, only for consumer electronics like laptops and gaming consoles to surge as people shifted to remote work and entertainment. Foundries redirected capacity away from automotive needs, exposing a terrifying truth: the modern world had become tethered to an intricate supply chain it understood only superficially, one capable of halting production lines and inflating prices worldwide. The crisis extended far beyond a single event, amplified by additional shocks that tested the resilience of human ingenuity. Unseasonably cold weather in Texas disrupted energy supplies to fabs, a severe drought in Taiwan strained water resources essential for manufacturing, an earthquake and subsequent fire in Japan damaged key suppliers, and geopolitical tensions, including the conflict in Ukraine, interrupted the flow of specialized gases like neon critical for laser operations in chip production. These factors converged into what industry leaders described as a perfect storm, resulting in over 11 million fewer vehicles produced globally between 2021 and 2023. With estimated revenue losses exceeding $210 billion for the automotive sector alone. Factories idled, dealerships emptied, and consumers faced longer wait times and higher prices, yet amid this hardship emerged a deeper appreciation for the unsung heroes of progress, the engineers and scientists laboring in sterile environments to restore the flow of innovation. This period of scarcity highlighted not only fragility but also the potential for renewal, as governments worldwide responded with initiatives like the United States creating helpful incentives to produce Semiconductors Act, channeling billions into domestic manufacturing to build more robust supply chains and reduce dependence on concentrated production hubs. Imagine stepping into a semiconductor fabrication plant, where the air undergoes filtration 10,000 times stricter than in a surgical operating room. A single rogue speck of dust could devastate an entire wafer, akin to a meteorite striking a bustling city. Here, in these cathedrals of precision, dedicated teams of engineers and technicians work in specialized suits, their movements deliberate and measured, surrounded by the low hum of machinery and the faint scent of purified chemicals. They sculpt at the atomic level, employing invisible beams of extreme ultraviolet light to carve billions of microscopic structures into wafers derived from the purest sand, transformed through chemical processes into crystalline silicon. The rhythmic pursuit of progress, once guided by the observation that transistor counts could double roughly every 2 years with minimal cost increases, a principle articulated by Gordon Moore in 1965, now collides with formidable physical boundaries. Early transistors, invented in 1947 at Bell Laboratories by John Bardeen, Walter Brattain, and William Shockley, and later integrated circuits pioneered in the late 1950s, propelled humanity into an era of unprecedented connectivity, powering everything from smartphones that fit in a pocket to artificial intelligence systems reshaping industries and medicine. Yet as nodes shrank toward 3 nanometers and beyond, the expense of designing a cutting-edge chip escalated dramatically, often surpassing $600 million, triple that of prior generations. At scales measuring mere atoms, classical physics yields to quantum phenomena, where electrons exhibit wave-like behavior, spontaneously tunneling through barriers that should contain them, leading to unwanted leakage currents that waste power as heat. To confront this challenge, the industry developed the gate-all-around field effect transistor architecture, a breakthrough that envelops the silicon channel completely on all 4 sides. creating a microscopic enclosure that exerts superior electrostatic control and prevents electrons from escaping. This innovation, first commercialized by Samsung at the 3nm node through its multibridge channel field effect transistor variant, allows for stacked nanosheets that can be tuned in width to balance performance and efficiency. Competitors like Taiwan Semiconductor Manufacturing Company and Intel followed suit, with the latter integrating it into its 18A process alongside other advances. Complementing this is the innovative backside power delivery approach, pioneered by Intel under the name PowerVia, which relocates the power network to the underside of the wafer. By separating power lines from the signal pathways above, engineers eliminate interference, reduce voltage drops, and achieve gains of approximately 6% in frequency alongside 5 to 10% improvements in cell density and overall power efficiency. These techniques represent more than technical feats, they embody the human spirit of perseverance, where teams of physicists, materials scientists, and process engineers collaborate across time zones and cultures to push the frontiers of possibility, transforming potential defeat into elegant solutions that sustain the march of computation. Central to these advancements stands a singular company in the Netherlands, ASML, whose high numerical aperture extreme ultraviolet lithography machines have become indispensable. The TWINSCAN EXE5000 and its successors, such as the EXE5200B, operate with a numerical aperture increase to 0.55 from the previous 0.33. Enabling single exposure features as fine as 8 nanometers and boosting transistor density by nearly 2.9 times. These systems demand an environment of flawless vacuum because extreme ultraviolet light at 13.5 nanometers wavelength is absorbed by air itself, and their mirrors, polished to atomic smoothness, if scaled to the size of the Earth. The tallest mountain would rise by less than 1 millimeter, reflect and focus the delicate beams with extraordinary precision. The anamorphic optics introduce a distortion that halves the effective printable field size from approximately 858 square millimeters to around 429 square millimeters. Yet this trade-off unlocks unprecedented scaling for the most advanced logic and memory chips. Intel became the first to install a commercial high numerical aperture tool in its facilities, with high-volume manufacturing anticipated in 2025 and 2026, followed closely by Samsung and others. This technological monopoly underscores both vulnerability and excellence, as global supply chains navigate export controls and strategic investments to ensure continued access amid rising geopolitical tensions, particularly around key production centers like Taiwan, which fabricates over 90% of the world's most advanced semiconductors. As monolithic designs strain against the physical reticle limit, the maximum area a single exposure can reliably pattern without prohibitive defect rates, engineers have embraced the era of chiplets. Rather than crafting one enormous die prone to yield losses, they assemble smaller, specialized modules like building blocks in a precise game of microscopic construction. The Universal Chiplet Interconnect Express standard, now advanced to version 3.0 as of 2025, serves as the universal language enabling seamless communication between these dies. It delivers bandwidth densities reaching terabytes per second per square millimeter, with data rates up to 64 gigatransfers per second, latencies under 2 nanoseconds, and power consumption around half a picojoule per bit, 20 times more efficient than traditional peripheral component interconnect express lanes. This modular approach allows pairing high-performance 3nm computational cores with cost-effective input-output blocks on 14nm processes, dramatically improving manufacturing yields and economic viability while supporting complex systems like those powering artificial intelligence accelerators from companies such as NVIDIA. The shift to chiplets not only circumvents physical constraints but also fosters collaboration across the industry, with over 120 technology leaders contributing to the open standard, promoting innovation and resilience in the face of escalating demand from artificial intelligence, data centers, and autonomous systems. Simultaneously, silicon reaches its limits in high-power and high-frequency domains, paving the way for wide bandgap materials such as silicon carbide and gallium nitride. Silicon possesses a bandgap of 1.12 electron volts, which falters under intense electrical stress, but silicon carbide, with a band gap around 3.2 electron volts and superior thermal conductivity of 5 watts per centimeter Kelvin. Thrives in environments exceeding 300 degrees Celsius. In electric vehicles, it enables 800-volt architectures that slash energy losses by up to 75%, support rapid charging times often under 20 minutes, and reduce the need for bulky cooling systems, thereby extending driving range and enhancing overall efficiency. Gallium nitride, boasting a band gap of 3.4 electron volts and exceptional switching speeds, powers compact chargers that occupy 1/3 the volume of silicon equivalents while maintaining high efficiency. And it underpins the radio frequency amplifiers essential for 5th generation and emerging 6th generation networks, as well as data centers where space and energy constraints grow ever tighter. These materials open new frontiers in aerospace, renewable energy, and industrial applications, where reliability under extreme conditions is paramount. Their adoption promises substantial environmental benefits by lowering global energy consumption in power electronics, aligning with broader sustainability goals as the world transitions toward electrification and smarter infrastructure. The convergence of these breakthroughs, subatomic transistor control, innovative power routing, precision lithography, modular architectures, and advanced materials, illustrates a profound evolution rather than an end to the principles of exponential progress first noted decades ago. Scientists and engineers worldwide, drawing from quantum mechanics insights and collaborative research shared through academic papers and reputable platforms, propose that future gains will arise from three-dimensional stacking. Complementary field effect transistor designs that layer N-type and P-type devices vertically, and hybrid integrations with emerging technologies like two-dimensional materials or even optical interconnects. Theories discussed in leading forums emphasize holistic system-level optimization, where software and hardware co-design, advanced packaging, and artificial intelligence-driven layout tools extend capabilities beyond pure dimensional scaling. This era marks not a retreat but a renaissance of creativity, where humanity architects around the laws of physics, turning potential barriers into pathways for greater efficiency, accessibility, and innovation that benefits communities everywhere. In practical terms, when facing situations akin to supply disruptions or technology bottlenecks, one can respond effectively by prioritizing the maintenance and upgrading of essential devices with components known for durability, such as those incorporating wide bandgap efficiencies for longer battery life and reduced heat. Support policies that diversify manufacturing locations to enhance global resilience, pursue education in science, technology, engineering, and mathematics fields to contribute to the workforce, and choose products from manufacturers investing in sustainable practices. For instance, in an emergency where a critical electronic system fails due to component scarcity, inspect for software updates that optimize existing hardware, source compatible replacements from verified suppliers emphasizing modularity. An advocate for community-level preparedness through diversified sourcing. These steps empower individuals and organizations to navigate uncertainties with confidence, fostering a culture of proactive stewardship over technological dependence. Delving deeper into the science, the transition from traditional planar transistors to three-dimensional gate-all-around structures addresses short-channel effects by providing complete gate encirclement, minimizing leakage to fractions of previous levels and enabling operation at lower voltages for power savings. Backside power networks further mitigate resistive losses, achieving up to 30% reduction in voltage drop in some analyses, while high numerical aperture systems discard multi-patterning complexities for cleaner, faster production. Wide bandgap semiconductors operate reliably in harsh thermal and electrical regimes due to their larger energy gaps, which require more energy for electron excitation, resulting in lower intrinsic carrier concentrations and superior performance. These advancements, grounded in rigorous experimentation at facilities worldwide, ensure continued progress while promoting energy conservation that benefits the planet and future generations. The channel Interesting Facts official remains dedicated to delivering such insights, blending rigorous scientific accuracy with practical skills and clear explanations that equip viewers to engage thoughtfully with the world around them. Through these explorations, we uncover not only technical wonders but also the inspiring resilience of human collaboration in overcoming challenges. What topic would you like the channel to explore in the next video? Perhaps a common error many make with everyday technology that could be avoided? Are you encountering any specific problem in daily life or online that requires clarification? Consider this situation: your new vehicle purchase is delayed indefinitely due to component shortages. What steps would you take to adapt? Would you choose option A, relying on a single advanced monolithic processor for maximum performance despite risks, or option B, embracing modular chiplet designs for greater reliability and flexibility? Share your preference and reasoning in the comments below. If this discussion has provided value, please offer a like and subscribe to the channel so we recognize your interest and continue creating meaningful content. In the upcoming video, we will examine a widespread oversight in personal device management that affects efficiency for countless users daily. Thank you for joining this journey into the heart of innovation.